This section is 4.3 area, and what we're going to be talking about in this section is the area of a plane region. So what I mean by a plane region is that we're talking about a two-dimensional object, and our two-dimensional object, we're finding a portion of area, and I've drawn here an example of one. We'll say that this starts at A, and it ends at B, and we're trying to find the area from A to be underneath this curve and sort of trapped between there and the x-axis. So one way we're going to be able to do this is think about what we know about area of plane figures in general. And there are some shapes that we know that are very easy to find area of. Rectangles is an example of one of them. So one of the ways we can approximate the area under this curve is by using rectangles. And there are three different approaches to using these rectangles, though, as we're taking a look. And so I'm going to show you those three different approaches. Basically, for the sake of argument, we could have a certain number of rectangles. In my pictures, I'm going to draw in 4 rectangles in all of them, just to give us a perspective of the problem. And so if we take a look at drawing sort of the vertical pieces for our rectangles, because we've already had the horizontal ones along the x-axis, the question becomes, if these are evenly spaced especially, where do we decide the height of our rectangles is? Now clearly, and we'll talk about this again more toward the end of the lesson, if we have more rectangles, we could get a better approximation. But there are 3 ways of approximating these rectangles. So let me take a look with you of the first way to approximate that we're going to look at the areas of, or the heights of these rectangles. So roughly speaking, this splits in half, and then we're going to split this in half again. Again, it's an estimate, sort of ballparking it with our eyes. We'll start with this value being x0. So this would be x1, x2, x3, and x4. So the first way we could do this is we could use the left end point. So that is, of this rectangle over here, in fact, sort of you could think of it over here, this rectangle, where do we want the height to be? Well, we select the height to be the left end point, so the left x0, the y value at x0, and we can sort of draw that height over and down. So there's our rectangle that we're going to approximate. And then the left end point of the second rectangle would be right here. The left end point of the third rectangle would actually be under the curve, and so would the fourth one. It would actually be over here as well. So if we're shading in what we have for our rectangles are right here. Let me try that in a slightly more opaque. Let's try that. There we go. That's a little bit better. So a portion of this is actually above the curve, and then a portion of this area sort of misses part of the area included as well. So we've got an overestimate in some areas, an underestimate in some areas, and those overestimate and underestimates will depend on the curve that we're using. So what we're going to, I'm going to give this a name L of x. Your book doesn't use this, but some resources will, just to designate, we're calling it the left end point. What we would do to find the area of a rectangle, of course, is we would multiply length times width, or sort of in terms of my picture, it almost looks like the base times the height. Now we're going to call the distance in between these, and we're going to do this so that it's evenly distributed as delta x, so the difference in the x values. So the width, or the base, is delta x, and the height in this case would be the left end point, so it's actually the y value, or the function value at x0. And then we want to do the same thing at the second rectangle, so the delta x, the base, times the height, which is the function value at x1. And then we can do the same thing, the delta x, of the function value of x2. And our final rectangle actually has a height of the function value at x3. Now notice the x, delta x here, is in every single term. So in sort of a way to consolidate that, what we could do is we could write that out in front and talk about adding up these particular y values, f of x0, f of x1, f of x2, and in this case we will end with f of x3. So in general, we'll kind of go down here and we'll rewrite this one more time. And this is a true statement, what I'm about to write, but it isn't necessarily the way we always think about it. But we talked in the last section about this way of writing a condensed form of doing summations. So the summations in this case would go from I equals 0 to 3 of f of xi. So it's just all of the y values, or the function values, from the x sub 0 value up to the x sub 3 value, and then we would multiply it by the difference between any two particular x values, the difference there, at the end to get the left bounded value. Now we can do the same thing with right rectangles. There's nothing special about my left rectangles. So if I do this with my right rectangles, let's take a look at what would happen. So we're going to cut the graph in half and then in halves again. Again, this is just ballparking it. We're not trying to be extremely precise. I'm going to show you, we're going to do a calculation here in a minute that's a little bit more precise. Now we're going to use the right endpoint. So we're going to start on the rightmost rectangle, just because it makes it a little bit cleaner to be drawing it, not because we would have to. But we've got this again, this x0, x1, x2, x3, and x4. And we're going to use right endpoints to estimate this now. So the right endpoint of this would be this right point. The right endpoint of the rectangle that is second to the right. The right endpoint of the rectangle that is the third to the right. And then the right endpoint of the rectangle that is the furthest left. And if we were to shade in this area, of course you see the underestimates on the left, and the overestimates end up being on the right on this particular one because of the type of curve that we're looking at. So these heights of these rectangles, we can notice again that we're going to get the same thing. We're going to multiply base times height. So very quickly we can identify that the r of x, or the right-hand value for estimating these, would be found by taking the delta x times each of the individual x values. So I'll skip writing that out on this one. But notice this case that the first value here is actually at x1. The second value is at x2. The third value is at x3, and the fourth one is at x4. We don't actually use the f of x0 value. So this is f of x1 plus f of x2 plus f of x3 plus f of x4. And the sort of abbreviated summation notation would look like it's the summation from I equals, in this case, 1 to 4 of f of x sub I. All right, we have one more method of approximating this, and this is to use midpoints. So again, we start with our same 4 rectangles that we did before. And again, there's nothing special about 4. We could be using anything. It's just easy for me to draw the 4. And so we're going to split it into 4 supposedly equal intervals. And then what we're going to use instead is on each of them, we're going to use the midpoint. So I'll label this as x0, x1, x2, x3, and x4. Now between x0 and x1 there is a halfway point, so we'll say it's roughly here, and then that's what we're going to let our height be on this particular one. And then in between x1 and x2 it's roughly here, so here's our height for this one. Between x2 and x3 we would be here, about the same height. x3 and x4 looks like right there, and so my height ends up being this one. So on this one you can see that it almost looks like it's a little bit underestimating and a little bit overestimating at the same time. And again, that sort of a description really does depend on the curve you're looking at, and I'm just using a generic. In this case it looks like a cubic curve to do this with. Now on this one I'm going to sort of avoid writing out all of my different notations. I'm just going to recognize here that we're still taking 4 rectangles and we're still adding them, but we're going to be using these x values to approximate the heights at instead. And so we're using the midpoints, the heights of the rectangle. All right, so we're going to do an actual equation with one now. So this one tells us our directions are to approximate the area under the curve on the given interval using the number of rectangles described and the evaluation rules. Those are the above sort of descriptions that we talked about. We're going to do it for the left endpoint, midpoint, and right endpoint. And I realize that that's sort of out of the order of what I described above. That's okay. We'll just do it in the order that your book uses. So they go from left endpoint to midpoint to right endpoint. All right, so this function here, we're going to start, and in general it's most helpful to start with a picture so that you have a reference of what this looks like. It doesn't have to be drawn, but it is helpful, especially at least the part of it that where we're talking about the interval we're doing this on. So this interval goes from 0 to 2, and it tells us that we are in fact going to use 4 rectangles. So since we're using 4 rectangles, we would split it in half, so that goes the value 1, and we would split it in half again, and this would be the value 1/2, or you could use 0.5, and the value 3/2, or you could use the value 1.5. All right, now this curve happens to look something like this. And if we were drawing in our rectangles, I want to avoid sort of putting in the heights of them because I'm going to be changing them based on the part of the problem I'm on. You can tell my picture is certainly not perfect. My rectangles do not appear to have the same width apart on the bottom. But of course they are, and if you take a look real quick, you can quickly decide that the distance between any two of these x values is in fact 1/2, or you could use 0.5 if you want to use a decimal. All right, so what we're going to do is we're going to find the left end points. So the left end point value for our rectangle, and we take the delta x value, right, that's the width of our rectangle, that's the 1/2, and we multiply it by the 4 leftmost endpoints. So if you take a look back at the picture, the left endpoints would be here, 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 and here. So it actually includes the x value of 0, 1/2, 1, and 3/2. It doesn't include 2. So this is going to be our function value at 0, plus our function value at 1/2, our function value at 1, and our function value at 3/2. And I do expect to see you write that down for me. There are some different features your calculator has the ability to do where it calculates this on its own, and some of you have that ability in your calculators and some of you don't. It's fine with me if you approximate this with your calculator to see what it's supposed to be and sort of see what your ballpark value you're supposed to be getting is. That's great. But I want to see the work that you understand the concept behind this. Now, you are going to also show me the next step, which actually finds each of these function values. You can plug these in one by one if you'd like into your function, or you're welcome to plug this function into y1 in your calculator. If all of this goes in y1 in your calculator, you can use your table to approximate this, which is a handy feature. I used my table to do this. My function value at at x equals 0 was 5. At x equal 1/2, I got 5.5. At x equal to 1, I got 7. And at x equal to 3/2 or 1.5, I get 9.5. So if you add these together and then you multiply by 1/2, you get an approximation for the area of 13.5 using the left endpoints. And if you take a look real briefly here, you can see that this is definitely going to be an underestimate, right? I mean, we've underestimated every single height for where the curve is actually hitting as we look from left to right. All right, let's take a look now at doing part B, which is the midpoint rectangles. So the midpoint rectangles, we use the same width. We use the same width on all of them. It's 1/2, a width of 1/2. But now we use the point halfway between each of these as the heights of my rectangles. For the heights of my rectangles, rather. So this would be a function value of 0.25, of 0.75, of 1.25, and 1.75. And again, you can use your table to evaluate that, which is a great feature. If you do, you end up getting values that are a little bit more detailed, a little bit longer numerical values. 5.125, 6.125, 8.125, and 11.125. Now if you add those together and then multiply them by that 1/2, you end up getting 15.25. Now the last piece we're supposed to do is to find the rightmost rectangle. So on this one, we're going to use the right endpoint. And the right endpoint would be the value 1/2, the value 1, the value 3/2, and now the value of actually 2. So we're not going to use the green part marks, we're not going to use the x equals to 0. So if we go with this sort of a perspective, r of x is the same 1/2 value, but we have the function value at 1/2, the function value at 1, the function value at 3/2, and the function value at 2. Those are the 4 heights of our 4 rectangles. And for each of those, the first 3 we actually already found. We found them up in part A. This is part C now, right? And so in part A we found that f of 1/2 is 5.5, f of 1 is 7, and f of 3/2 is 9.5. So we can use those again. So 5.5, 7, and 9.5. And then if we plug in the value of 2, we actually will find that we get 13. Again, add those together and multiply by 1/2 or divide by 2, and we get 17.5 as an approximation using the right end points as the height of our rectangles. And each of the problems that you're working for your homework will have this sort of a variety to them. You can use the table for your function. If you have more than 4 intervals, that's okay. It just means that you're going to have more than 4 function values. So if you had n equal to 8, you had 8 rectangles you were forming, you'd have 8 function values you're adding each side. The picture really helps you more to determine the spacing of them, and the delta x value, this 1/2 we got from this one, that's also helpful for that. And then also finding out which values we're actually adding together. In this case, those 4 of them that I just marked in red would be on part C on this one.